Hi, I'm Abdul. I'm an engineering manager at Credit Karma. I'm on the machine learning team. Our main objective is to make machine learning at scale accessible and easy to use throughout the company. Today, I'm going to talk to you about how we've used Spark DataFrames to build models to serve personalized recommendations for our members. Those models often optimize for different objectives or compete against each other to provide the best recommendation. First, I'm going to briefly go over the recommendation problem to kind of motivate why we need to build models to serve recommendations. I'm going to tell you two stories today. One is about our hypothetical member, John, that will kind of further demonstrate the different aspects of the recommendation problem. The second story is about two models and how the choice of your model evaluation metric can be really important for highlighting bad models before you deploy them in production. Then I'm going to talk about how we've implemented wrappers around data frames to provide compile time type safety. And finally, I'm going to go through some gotchas that we ran into while developing our machine learning environment. So Credit Karma is a fintech company. We serve over 60 million members to help them make financial progress by providing free access to their credit scores and full credit history. We make money by recommending financial products. We usually get paid when the member is both interested in an offer and they actually get approved for that offer. We serve recommendations in different verticals, credit cards, personal loans, auto, which includes auto insurance and auto refinance, mortgage, and this year we launched our free tax filing product. One of the goals of data science and machine learning at Credit Karma is to serve recommendations that our members are interested in, that they have high probability of being approved for, and that have long-term benefit for the members. For example, using a personal loan that usually has a lower interest rate to pay off credit card debt. Now, those different objectives are usually competing objectives. And that's what differentiates the recommendation problem at Credit Karma from what we see at other companies. So now I'm going to go over John's story to kind of demonstrate the different aspects and the competition that happens between the models to serve the recommendations. So what do we know about John? We know he has good credit. He recently got in a car accident. He was low on cash, so he needed to use his credit cards to pay for car repair. John logs into the Credit Karma application. Let's see what we can recommend for him. Not surprisingly, rewards cards or reward offers our members are really interested in them. We all love cashback, right? So we know that if we recommend the black offer for John, he will have high interest in that offer. John also knows that he has to reduce his interest payments. So we know, based on people in John's situation, people that have high balance on their credit cards, that if we recommend a 0% APR transfer card, John would be interested in that. However, from a recommendation system standpoint, it makes sense to recommend actually the black card for John in this case. Also, you can see here that how the probability of the member's interest conflicts or competes with the probability of being approved. This is because banks and credit card issuers usually use incentives to entice high credit score users. Those incentives could be in the form of rewards or 0% interest and intro interest to have them apply for those offers. Lower credit score users also want to apply for those offers, but usually have a lower probability of being approved. It gets more interesting when we take into account the long-term benefit that we can expose to our members, such as John. So here, if we provided some context around why we would recommend the green card offer for John, John may have much higher probability of being actually more interested in that offer. So we recommend that green cards offer to John, and we declare that we achieved success. Did we, though? What about other offers or other types of verticals that we can recommend for John? For example, let's have our best credit card offer compete with a personal loan. Personal loans usually have lower interest, and that could be beneficial in John's situation. So depending on the balance that John has on his cards and how fast he can pay them, it may be more beneficial to actually recommend a personal loan for John. Now, I told you John's story to show the competition that happens among models. For each stage, for each offer, and each stage is driven by a model. So there's competition among models within an offer. There's competition among models across different offers within a vertical. And there's competition among models across different verticals. So in John's story, we only had a handful of models. However, we experiment each month with thousands of models to make sure that we continue to serve the best recommendations for our members. So it's very critical for us to make sure that those models, when competing, they compete against each other nicely. And my second story is going to put some more context on what I mean by compete nicely. So let me make a couple of simplifying assumptions here. Let's assume that we're only interested in modeling the member's interest in a card. So that was the first stage from the previous slides. And also, let's assume that we only have those two offers. So we have the prediction column here is the probability of a member being interested in that offer, and the label is 0 when the member is not actually interested in that offer, and 1 when otherwise. Let's arbitrarily pick the AUC, or area under the ROC curve, as our evaluation metric. Using that metric, our guess is that those two models are great models because they achieve the best possible value that you can achieve. There's a problem here hidden. Can anybody spot an issue here? So it actually turns out the green cards offer did a terrible job in its second prediction. It predicted 90% probability of the member being interested in that offer, when actually that was not the case. So depending on how frequent that is, this could be a problem. This model could be overconfident and not calibrated well. However, we have billions of impressions, billions of rows that we're training on, so we don't really know this. We only have the signal from our evaluation metric, which tells us that those two models are both great models. So we proceed with and deploy them in our recommendation system. And we start serving recommendations for live traffic. Naturally, here it makes sense to recommend or show the offer that has the highest predicted value. So based on what we know from the previous slide, what do you guys expect the impression distribution? Which offer would get more impressions? We know that one of the offers was overly confident. It's telling the recommendation system that, give me more offers, I'm confident that the user will interact with me or will be interested in me, when that is not necessarily always the case. And that offer is actually the green offer. So the green offer would be kind of cannibalizing traffic away from the blue offer. And depending on the severity of that situation, we may end up achieving worse results than random if we just pick out offers with the same probability randomly and showing them. So let's go back to our two models and our metric. We know that AUC was not a really good metric. There was an issue, and we couldn't highlight that. What kind of metric should we use? We know the problem is that the green cards offer is both highly confident and wrong. And there's a specific metric that actually penalizes exactly that. And that's the logarithmic loss, or log loss. A lower log loss is better, so we can see that the blue cards offer has a better, is better based on that metric, and the green cards offer is actually worse. It turns out actually that a trivial model that always serves the average probability, in this case would be 1/3, so regardless of the feature set, if it always gives a probability of 1/3, will achieve a better log loss than what the current model for the green offer achieves. Another thing we do at Credit Karma is look at calibration plots. I've just been at the Yelp talk, and they also do some look at calibration plots. It's essentially the idea is the same, but they take the difference between the two lines. So to build those plots, essentially we score the test data. We sort it by predicted scores, and we divide it into buckets. In this case, we have 3 buckets. Within a bucket, we average both the predicted scores and the actual labels. The actual labels gives us the experience probability, and the predicted scores give us the predicted probability. So here, it's really obvious that where the model is misbehaving, in bucket 1, there's a huge discrepancy between the actual and the predicted. This shows us where the model is being overly confident. Ideally, you want those 2 plots or 2 lines to align. So this, using log loss, using calibration plot, we know that the model is bad. And this is where the investigation begins. Maybe we need to get better data. Maybe we need some hyperparameter tuning, different algorithms, et cetera. So the 2 models I've shown are really simplistic models. However, the models that we build at Credit Karma are much more complex. We have thousands of features, terabytes of data, models consisting of an ensemble of different trainers. It could be different levels of gradient boosting trees, wrapped with a logistic regression, et cetera. So it's really critical for us that we both achieve scale because of the size of the data and type safety because of the complexity of the models. Fortunately, scale or data frames help us with the first problem, which is scale. Now I'm going to talk about how we achieve type safety around data frames. So data frames were introduced in 2015, back in version 1.3 of Spark. As many of you may know, the 2 main advantages are ease of use and performance. The ease of use comes from the fact that data frames are flexible data types. They can have any number of columns, any type within those columns. So there's not much type checking done at compile time. However, some checking could be done at runtime using the attached schema. To show why the lack of compile time type safety it could be a problem, I'll show this example. Here, since we're doing supervised training, our do training function takes a data frame that has both features and labels. However, from the data type that's passed in, that's not explicitly stated. We have 2 data frames, one that actually has features and labels, and one that has only features. And somebody mistakenly calls that do training function with features only data frame. So it could be hours until you hit this in your job, until you hit this point where a runtime exception could be thrown. So that's a problem, and we want to try to fix it. The basic idea is that we introduced 2 wrappers. One is a wrapper around a Spark SQL row, and the other is around the data frame itself. In this example, the row consists of features and labels, and the parse row function of that case class, which indicates that it's features and labels, knows how to parse a Spark SQL row and turn it into an instance of that case class. So as soon as we read in our data into a data frame, we map it through that parse row function which returns an RDD of features, labels, data row. We pass that RDD into our data frame wrapper, which also indicates that it's a data frame of features and labels, and that transforms it back into a data frame that we know has the correct data, or the data that we expect. So now, instead of passing around data frames and having function parameters being typed with a data frame type, we can explicitly call out what kind of data we're expecting in that function. So let's go back to our previous example. So this time, I modified it to include those different types where we used to have data frames everywhere. Somebody does the same mistake, tries to call the do training with features-only data, and this is now a compile time error because that type doesn't match what the do training function expects. We all know that working with Spark could be challenging at times. So we've run into kind of out-of-memory issues or Stack Overflow issues. So I wanted to share a few issues that we ran into and hope that can help you avoid or solve some potential issues that you can run into. So specifically, I'm going to go over 3 errors or issues that we ran into. The first relates to a left join. Let's assume here we have 2 data frames. One that has, let's say, billions of impressions. It has a click ID that joins to another data frame that has additional information about the clicks. We want to join in the click data with the impressions, but we don't want to lose any of the impressions. This is a classical left join scenario. Fortunately, that could be accomplished by simply one line of code by passing the left outer parameter to the data frame join function. However, there's a problem here. What do you guys expect will happen when we run this line of code? And this time, I'm going to actually try to see if anybody can take a guess on that. The hint here is that there's a key skew somewhere. Sorry? Same name of columns? All right, can you step up to the mic?
So as you said, there's a data skew because we'll have in the impression table a lot of click ID is none.
Yes, exactly. So just to kind of explain that in more detail, how Spark, how it does the join, it actually does a shuffle first to have all the keys that are the same value be on the same executor. That makes it more efficient to run. So that since most of our impressions don't have clicks, all of those will go into one executor on one machine, and you'll likely run out of memory, or your job will be really, really slow. The natural instinct here is to throw more machines at it. Unfortunately, that doesn't help. So the solution is actually simple. You divide the data frame into 2, one that actually has clicks and one that doesn't. You inner join the one that has clicks with the click data, and then you union back the impressions that do not have clicks. So we use gradient boosting tree training a lot at Credit Karma. As we increase the number of iterations on our trainer, we run into this following error. It's essentially a Stack Overflow somewhere in the Spark SQL Catalyst package. And the reason for that is that each iteration of a gradient boosting tree runs a lot of operations on the data frame. And that increases the lineage of that data frame and eventually causes the Stack Overflow problem. So one fix is to, so checkpointing is known to break that lineage. And this is how you can tell that GABT regressor trainer to, or you can specify the checkpointing interval, and you can reduce that to break that lineage and avoid this error. Another way, kind of a Band-Aid fix for this, is to increase your thread stack size by passing this Java options parameter to your executor. So the final issue I wanted to talk to you about today relates to Spark SQL code generation. So when we run a simple, or as we increase the number of features or rows on our data frames, we run into this nasty error. It's essentially saying that the Spark SQL code generation generated a Java method that has size more than 64 kilobytes. That exceeds the size allowed by the JVM. You can replicate that by this simple example. Essentially, here we have a data frame that has 500 columns, 1,000 rows, and we're trying to do a simple operation such as a random split on that data frame. And this is where, when you evaluate that, that's where it crashes. So the fix is actually to upgrade to one of those Spark versions. And there's more detail in that link. So the two main takeaways I want you guys to go with today is first, that you be very careful when you're choosing your model evaluation metric. Make sure that that's a conscious decision and that maps well with what you're trying to optimize for. I hope your takeaway is not to use log loss blindly, but rather, like I said, think about what you're trying to optimize. For example, let's say if you had a list of sales leads and you want to rank them in order that you want to pursue them in, then actually AUC may be a good metric for that. In our case, when we had competing models and we wanted to make sure that the models are calibrated well, log loss actually turned out to be a better metric. Second takeaway is that there's ways to introduce type safety around dynamic data types. I've shown you how I've done that with, or we've done that with DataFrames. Thanks for listening. Visit our engineering blog at engineering.careerkarma.com. Some contact information for me if you want to follow up afterwards. And right now, I'll take questions.
Just put your hands up and I'll run around.
Hi,
Hi.
This is Vikas. So we also use Spark, and there is one specific case, right, when you just showed about that skew in the join and all, right? We kind of solved this problem. We also encountered this problem. This is one of the very common ones, right,
yeah.
which happened. So probably, what are your ideas about, like, did you guys try like repartitioning the bigger data frame altogether? Because even if you just go ahead and just do the repartitioning, that also really helps. So you can just say that my bigger data frame, which is having this queue itself, if it is repartitioned across, let's say, some 1,000 partitions or all, then yes, your number of executors are going to increase, but still, your problem of having the same key on the same machine, that just goes away. Because then the other, yes, the limitation is that the other data frame has to be, which has to be joined, has to be small enough as well.
So if I'm understanding correctly, you're saying if you pre-partition and increase the number of partitions on the impressions,
the bigger data frame,
that
yes,
issue would go away.
That issue, but for that, the precondition is the other data frame with which you are trying to join has to be small enough so that it can be.
You want to do a broadcast join? Is that what you're saying? Okay,
yes.
So that could be. It depends on how small the other data frame is.
Yes,
like if you're Plex data, and that's in that case, I don't think you would run into a key skew issue.
Yeah, because
yes.
then you would have partition one already, and then the both side of those shufflings can be avoided.
Correct. But to be clear, that if you didn't do that, like however you repartition that big data frame, you still run into the key skew. And I think actually the more partitions you have, you may even run into that problem even more. So.
Yeah, I mean that depends on cluster size as well.
All right. Thanks for sharing that.
Thanks for your presentation. So in your slides, you mentioned that for the models, there's possible 3 models to be built. One is for interest, the other one is for approval. Then the last one, which could be in terms of long-term benefit. Given that the 3 models somehow can compete with each other in terms of score, So how you will be able to prioritize these three models outcome and provide the best of the recommendations or suggestions to your customers?
Yes. So actually, I mean, all of them are critical because our model is that we want to get the person to actually be both interested and approved. So we need to, a lot of different applications, they optimize for click-through rate, right? That doesn't actually work for us. So we need to actually take into account that deeper stages of the funnel too, and make sure that along the way we don't have any anomalies. Otherwise, our overall performance would degrade pretty significantly.
All the way back here. Who was it again? Oh, there we go.
You mentioned using data frames for the type safety. I was wondering if you've considered using data sets.
That's, we did actually a lot of the code so data sets became more mature in Spark 2. We tried to use them in Spark 1.6. I highly advise you not to do that if you are 1.6. So this approach came from that. And also, I think the Spark ML libraries, they kind of tend to favor data frames. It's easier to work with data frames if you're in a machine learning environment and trying to build models based on your data. So that's the main reason, but you're correct. Like data sets are a good way to provide that compile time safety while not sacrificing performance.
Yeah, thank you.
Any other questions? We still have 3 minutes, so don't be shy. All right, just to follow up with that last one, data sets were experimental in 1.6, but now they are, they lifted the experimental tag in 2.0, so feel free to use them.
All right.
Any other questions? If not, oh, one more.
Vikas again. This is about, so with data frames, right? In your experience, have you ever faced those kind of requirements wherein, let's say, when you're persisting the results, right? Many times, it depends how are you consuming even the outcome of the analytics, whatever you're doing. Many times you might be feeding it somewhere, or many times you might even be persisting the results back into, let's say, some Hive data store or something, right? So are there any specific recommendations which you have on those lines? Because we clearly have seen those kind of issues, like, for example, ORC plus zlib versus ORC and Snappy, and Avro plus Snappy, and you have multiple of those choices, right?
Yeah.
It just changes without even a single line of logic change. It just changes the performance drastically.
Yeah.
22 hours versus like 22 minutes. We have seen those kind of situations.
In my experience, we use Snappy compression and Parquet format. You may squeeze a little bit more. So the real cost is actually computation. So we're really so you can save some space by when you persist it, but actually storage is cheap nowadays. Reading the data and uncompressing it, which consumes a lot of CPU time, could cost significantly, or that could be the major cost for you. So in that case, Snappy is actually a good kind of medium. That's in our experience. That's what we use. gzip kind of is more compute intensive. And you can see that your job just takes a long time until it uncompresses all this data. And it's actually not splittable either, because so that it needs to read the whole file, uncompress it, then decide how it needs to kind of distribute that. So unless you're really, really conscious or really sensitive to cost of storage, I would avoid the gzipped data. All right?
All right, I think we're at time, so please give a big round of applause to Abdulla.
All right.
Thank you very much.